Hello, this is Mr. Wynn, and this video is over geometric sequences and series. So a sequence is just a list of numbers that follow a pattern, like before. A sub 1 is the first term, A sub 2 is the second term, A sub 3 is the third term, all the way to A sub n, which is the nth or last term. A geometric sequence means that the pattern used is a common ratio. Ratio means multiply, so that means you're going to multiply or divide by the same number over and over again. The formula for the common ratio, R, is A2 divided by A1, so the second term divided by the first term. Now you can use any two consecutive terms. You could do the 10th term divided by the 9th term, or the 4th term divided by the 3rd term. Here's an example. 2, 4, 8, 16 is a geometric sequence where R, which is 4 divided by 2, so that's the second term of the first term, is 2. I can also do 3rd divided by 2nd. 8 divided by 4 is also 2. Or I can do 4th term divided by 3rd term. 16 divided by 8 is also 2. Because 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. It follows the times 2 the entire way. Here's another example. 12, 6, 3 is a geometric sequence where R can be 6 divided by 12, which reduces to 1/2. Since that's less than 1, it's going to get smaller. 12 times 1/2 is 6. 6 times 1/2 is 3. Here's a non-example. 3, 9, 18 is not a geometric sequence because there's no R, there's no common ratio. If I tried second divided first, 9 divided 3 is 3. I tried third divided second, 18 divided 9 is 2. Those are different numbers. I can't do times 3 then times 2. It has to be times 2 all the way, or times 3 all the way, or times 1/2 all the way. Like before, our first step is always trying to find that common ratio R. In the other case, it's common difference D. And if you here's the graph, if you plot this, a geometric sequence will follow an exponential graph. So X is the term number, first term, second term, third term, fourth term. The Y is just any geometric sequence. I tried the first one, 2, 4, 8, 16. This will follow an exponential graph. Now, remember, it's just dots. It's disconnected. It's not connected. All right, sometimes instead of getting a list, you get an explicit formula. Like before, you're just going to plug in those values, 1, 2, 3, all the way till n. So here's an example. Determine the first 3 terms and the 6th term of a sub n equals 32 times -1/2 to the n minus 1 power. This is like a times b to the x power. So I plug in 1 for n. This will be the 1 minus 1 power. It's 0. Anything to 0 power is 1. So 30 times 1 is 32. If I plug in 2 for n, 2 minus 1 is the first power. It stays the same. 30 times -1/2 is -16. I plug in 3 for n. 3 minus 1 is 2. That's squared. -1/2 squared. -1/2 times -1/2 is positive 1/4. 32 times positive 1/4 is 8. I plug in 6. 6 minus 1 is 5. -1/2 to the 5th power. That's odd number negative, so it stays negative. Then 2 to the 5th is 32. 32 times -1 over 32. The 32's cancel. You get -1. So for this sequence, it would actually be 32, then -16, then 8, then whatever, all the way to -1. All right, sometimes you get a list, and you must find a specific term. There's a formula for this as well, called the nth term formula, just like for arithmetic sequences and series. Our nth term formula here changes. It's going to follow an exponential formula. It is a sub n equals a sub 1 times r to the n minus 1 power. A sub 1 is the first term, a sub n is the last term, n is the number of terms, r is a common ratio, and like before we went to 3 of the 4, you don't be missing one of these. That missing thing you'll find by using the formula. So here's just find the 8th term of the following geometric sequence. 5, then -10, then 20, then -40, then whatever. So what do we know? The first term is 5. R, way to calculate, second divided by first. So -10 divided by 5 is -2. It's more than 1, so it's a multiplier. So 5 times -2 is -10. -10 times -2 is positive 20. 20 times -2 is -40, and so on. They want the 8th term, so n is 8. We don't know what that is yet, so I'm going to fill in the formula. So a sub n is really a sub 8. The first term is 5. R is -2, and our exponent n is 8 minus 1. You can type in the calculator, you'll get the answer right away. I'm going to simplify it. 8 minus 1 is 7. Then I do -2 to the 7th power, you get -128. Then I multiply 5 times -128 to get -640 is our 8th term. We also have geometric means. Those are in between numbers following the geometric pattern. That nth term formula will also help us here. Again, you must know 3 of the 4. So a problem says find 3 geometric means between 3 and 48. So there's going to be 3 blanks between 3 and 48. So what do we know so far? We know the first term is 3. We don't know what the multipliers are. We know there's 5 terms. There's 1, 2, 3, 4, 5. We know the last term is 48. I'm going to fill in the formula. So the last term is 48. The first term is 3. We don't know what r is. And the exponent will be n minus 1, which is 5 minus 1. Fix that. That'll be to the 4th power. get r by itself by dividing by 3 to make 16. Then fourth root both sides. And you can do tree branch, but you get 2, a group of 2. Remember, if it's an even root, you must have plus or minus. That's very, very important here. So there's 2 values of r here. If r is positive 2, 3 times 2 is 6, 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48. It matches, it works. If r is negative 2, 3 times negative 2 is negative 6, negative 6 times negative 2 is positive 12, positive 12 times negative 2 is negative 24, negative 24 times negative 2 is positive 1. That also works. There's 2 answers here. Like before, we have a series. A series is still a sum of every term on that list or sequence. There's a formula for this called the geometric sum formula. There's 2 of them. They're the same formula, actually, but one's easier to use than the other depending on the situation. A sub 1 is the first term, A sub n is the last term, n is the number of terms, r is the common ratio, and s is the sum. So here's an example. Find the sum of the following geometric sequence, 3, 6, 12, 24. So we're basically just adding those 4 numbers. In a calculator, you type in and get 45. But again, it's not going to be a short list. I could put 50 terms in here or 1,000 terms in here. You're not going to write all 1,000 terms. Use the formula. So here's what we know. We know the first term is 3. We know the last term is 24. There are 4 total terms. And then r, which is 6 divided by 3, is 2. I can now use either formula. So let's do this one first. I plug in the first term, 3, minus the first term, 3, times r, which is 2, to the exponent, 4, over 1 minus r, which is 2. I just type that in the calculator. I get 45. Let's try the other formula. Here, the first term is 3, minus the last term is 24, times r is 2, over 1 minus r, which is 2. Type in the calculator, I also get 45. Alright, so you use either formula. It depends what you have or what you need. This first formula needs the first term, the common ratio r, and the number of terms. It does not need the last term. So I never use 24 in this formula. Over here, I use the first term, last term, and r. I did not use n. I did not need the number of terms. I did not use this 4 right here. Alright, so depending on the situation, sometimes it's easier to use this formula. Sometimes it's easier to use the other formula. Sometimes you use both formulas together. So we have the nth term formula and we have the sum, both sum formulas. So here's an example. Find the sum of this following geometric sequence. It starts at 2, then it goes to 4, then 8, then blank, all the way to 512. Now, let's see what we know. We know that A1 is given. The first term is 2. R can be quickly found. It's going to be second divided by first. So 4 divided by 2 is 2. N, the number of terms, requires some work. We're going to use this nth term formula. And actually, because we don't know what n is, it's going to require using logarithms. So it's going to be a lot of work for this problem. Not always. Sometimes you can use radicals of the roots, like fourth root or whatever. And then the last term, an, it is given to us. It's 512. I know a1, an, and r. So actually, I can use the second formula without having to do any work at all. No need to use this first formula. Although I could use it to find the number of terms, which again, we don't know yet. So I'm going to use the second formula. I don't need n. I just need the first term, 2. The last term, 512. The common ratio, r, is 2. And then over 1 minus r, which is 2. Type in my calculator, I get 1,022. All right. We also have sigma notation again, read the exact same way. So remember, you see this E symbol, that's sigma. That's the summation, tells you to add everything up. The bottom tells you the variable and what number to plug in for that variable. So 2 is the first value I plug in, and it goes up by 1. So then 3, then 4, then 5, then 6, and 7, all the way to this last number up here, 8. So 2 through 8. And then this on the right side is the formula we're going to use. We're going to plug in 2 for x, 3 for x, 4 for x, 5 for x, 6 for x, 7 for x, 8 for x. If you do the long way, hopefully you do the shortcut. So here's an example. Find the sum of this geometric series. So the sum of this from 2 all the way to 8. So option A, like before, I could plug in x is 2, then 3, then 4, then 5, then 6, and 7, 8. Then add all those numbers. However, it's going to take way too long. And again, it's not always going to be a handful of numbers. It might be 20 different numbers or 30 different numbers or 100 different numbers. So option B, the formula is much faster. Let's just find the first term, the common ratio r, and the number of terms. So the first term is easy. You just plug in the bottom number 2 for x. So it would be -1 times 3 to the 2 minus 1. Well, 2 minus 1 is 1. 3 to the first power is 3. -1 times 3 is -3. I found my first term. I'm going to find r. R is actually given to us. R is this multiplier without the exponent, or with the exponent. Type it right there. And then I need n. If you see sigma notation, n is the easiest to find. You just do top minus bottom plus 1. So this 8 minus this 2 plus 1. So 8 minus 2 is 6 plus 1 is 7. There are 7 terms here. Because really, if I plug in 2, 3, 4, 5, 6, 7, 8, that's 7 different things I plug in. There's 7 different numbers. I have the 3 numbers. I use this formula. The first term is -3 minus the first term again is -3. I put in parentheses. R is also 3. Exponent is 7 because it's 7 terms. Over 1 minus R is 3. To my calculator, I get -3279. All right, 2 more slides. We have infinite geometric series. And if it's an infinite list, that means it never stops going. It might have a finite sum, might not. It depends on the common ratio R. The formula for infinite sum, S, is the first term divided by 1 minus R. And this only works if R is less than 1. That's the absolute value of R is less than 1. So it's between -1 and +1. All right, so here's an example. Find the sum of this infinite geometric series if it exists. Notice I did not give you a final number because it keeps going. It goes 1, then 10, then 100, then 1,000, then 10,000, then 100,000, then 1,000,000, then 10 million, 100 million, a billion, so on. I find R. Second divided by first. 10 divided by 1 is 10. So it's being multiplied over and over by 10. Because this value is more than 1, an infinite sum doesn't exist. Because whatever you add up, the next number is going to be even bigger than that because it'll be 10 times larger. So once you add 1,000,000, then you add 10 million, then 100 million, then a billion, then 10 billion, and so on. So it's just grow like crazy. So you cannot give me the exact value. But on the second problem, find the sum of the following infinite geometric series if it exists. It goes 1,000, then 100, then 10, then 1, then 0.1, then 0.01, then 0.001, then 0.0001. All right. Hopefully you notice divide by 10, but you do the formula R is second divided by first. So 100 divided by 1,000 is 1/10. That's why it's getting 10 times smaller. Well, because R is less than 1, it's really 0.1. And if some does exist, really, because when we get divided by 10 and we keep dividing by 10, it gets so small, it basically gets really close to 0, around to 0. It'll be negligible. So we use the formula. The first term is 1,000 over 1 minus R, which is 1 over 10. I type in the calculator, I get 10,000 over 9. If you're curious about the decimal, it'll be 1,111.1111. Because really, here's 1,000, then 1,100, then 1,110, 1,111, and then the decimal keeps going on. It will never get bigger. All right, last slide. Make sure you read the same thing, infinite geometric series, in sigma notation. The same formula, it only works if R is less than equal to, or less than 1, not equal to 1. So find the sum of the infinite geometric series if it exists. Well, what's going to be is sigma notation. The bottom is your first amount. The top is your final amount. The top says infinity. You can't plug in infinity. So this means infinite geometric series. You look at R. R is right there. The multiplier with the exponent. R is 7. Because it's 7, that's more than 1. It doesn't exist. For the second problem, try again. This is infinite because it goes infinity. You can't plug that in. R is this 1/3. Because 1/3 is less than 1, we do have an infinite sum. I need to use this formula. I need to know the first term. To find the first term, you plug in this bottom number, 2, for n. It could be any letter. It could be k, n, x, y, whatever, I. So it'd be 9 times 1/3 to the 2 minus 1. 2 minus 1 is first power. 1/3 to the first, 1/3 times 9 is 3. Now we know the first term is 3 over 1 minus R is 1/3. Type in my calculator, I get 9 over 2, which is 4.5 of the decimal. And that's it. Thanks for watching. If you have any questions, make sure you ask in class. See ya. Bye.